Today we are going to perform our fifth recitation, online recitation, and we are going to deal with some questions about Euclidean domains, Euclidean functions, some prime elements, and some questions about ideals. And lastly, maybe we can solve a question about a Euclidean, unique factorization domain. Okay. Have you? I think you watched all the videos of your instructor. So if you have any questions, please do not hesitate to interrupt me and ask your questions immediately. Okay. If you don't have any questions right now, we can start with my questions. Okay. Do you have any? No. Okay. The first one is that prove that Z root 2 is a Euclidean domain. Euclidean domain. As you know, Euclidean domains are integral domains at first. Then we should have a Euclidean function on it, satisfying some property, and we should perform actually the division algorithm here in these rings. First, let me start with explaining something. That root 2 is an integral domain. Why is that so? Because it's a subset of real numbers, right? And Z root 2 is a subset of R, for example. And we should define a function on it. We're going to call it as the Euclidean function. Consider the map here. Consider the map. I'm going to denote it by n because it has some good property and related to some different name. Norm, it's called. And this is from our original ring to non-negative integers, okay? And what does it do? It takes a plus b root 2 to absolute value of a squared minus 2b squared, okay? This absolute value is important here. Now, it is easy to check that it is multiplicative. Check that. Okay, here. Check that. And xy is equal to nx times ny. That is, n is multiplicative. Okay. And now, to be sure that Z root 2 with this map is a Euclidean domain, we have to show that it actually allows us to perform division algorithm over this ring. Okay, so we need to show the division algorithm. We need to show the division algorithm. Okay, so for this purpose, let us take two elements from our ring. Let x be a plus b root 2 and y be c plus d root 2 in z root 2, the arbitrary elements. Okay. Now let us look at the quotient. X over y. What is this? It is just computation here. A plus b root 2, c plus d root 2, and if you apply multiplication by some kind of conjugate of c plus d root 2, conjugation like complex numbers, but here we have, instead of I, we have root 2. So somehow we are trying to get rid of this root 2. Okay. So just divide and multiply by c minus d root 2. Okay. C minus d root 2. This is something like we are trying to obtain this kind of a squared minus 2b squared kind of thing here. Okay. And trying to make all coefficients integer. Okay. So if you perform this multiplication, what we have is that AC minus 2BD plus BC minus AB root 2 over C squared minus 2D squared. Okay, let us call it as R plus S root 2. Of course, these coefficients R and S, let me write them down, where R is equal to AC minus 2BD over C squared minus 2D squared, and S is equal to BC minus AD over C squared minus 2D squared, okay? These may not be integers, so we have to do some more work. Now, let n be an integer. It is not just straightforward proof. We have to do some manipulations, okay? Now let n be an integer closest to the rational number, r, closest to the rational number r, and m be an integer closest to the rational number s, such that we have one more condition. The absolute value of r minus n, that is the distance between these two numbers, is less than or equal to 1 over 2, and the same should be true for the distance between s and n. Okay? We can choose such numbers, right? We can choose an integer, and we can, our choice may be made as close as we like. Okay, so we are choosing such integers. Okay, and what we have is that let t be r plus s root 2 minus n plus n root 2. As you can guess, our candidate for the remainder would be this one, because we know that n and m are integers. So if we divide this a plus b root 2 by c plus d root 2, now our claim is somehow that our remainder will be this one, n plus m root 2. Okay, so let us expand this by using our terms x and y, a, b, c, d, x over y minus, this is r plus s root 2. We've seen it here. Okay, x over y is nothing but r plus s root 2. So instead of r plus s root 2, we are writing x over y. Okay, here we have two more people here. Okay. What was it? Yes, n plus m root 2. Okay, and if you multiply each side by y, we have yt is equal to x minus n plus m root 2 y, right? Okay, now we get rid of all rational numbers, and now here we are with integer coefficients. Yt is integer. Yes, it is. Yes, because what? Why? No, not an integer, but an element from z root 2, right? So if you consider both sides of the equality, these are elements from z root 2. Okay? Any objection to this one? No? Okay. So if you take this x out, to the one side of the equality, then we have n plus m root 2, sorry, not a remainder but a quotient, that this one, y plus yt with n plus m root 2 is from this one. Let me put a star here, okay? So for the Euclidean function, what should we show is that the norm of the remainder should be strictly less than the norm of the divisor, right? Or it has to be 0. Now, if we apply our Euclidean function to this t, and we are going to obtain some kind of inequality here. Norm of t, maybe it is better to write it down just here. I don't know. Here, let me put first t as r plus s root 2 minus. Is it minus? Yes, it is minus. Minus n plus m root 2. Instead of this one, I'm going to use r minus n plus s minus m root 2, something like this. Okay. Now, if we apply your Euclidean function to both sides, then we have n of t. This is our function. This is, of course, here we should first say that root 2, of course, can be considered as a subset of q root 2. This is the just the inclusion, so you can use this function inside this one also. So this is nothing but r minus n squared minus 2 times s minus m squared. And we have chosen these n and m such that the absolute value of r minus n is less than or equal to 1 over 2, and s minus m is less than or equal to 1 over 2. Okay, so this is less than or equal to r minus n squared plus, this is just the equality, you know, triangle inequality, 2 times s minus m squared. And so this is actually less than or equal to 1 over 4 plus 2 times 1 over 4, which is 3 over 4. Okay, now we know the multiplicative property of m as, let me write, as n of alpha times beta is equal to n of alpha times n of beta. You're going to check it. If you compute the function value of y times t, then you can write this as n of y times n of t. And we know that since n of t is less than or equal to 3 over 4 here, we have found it. So we can write this one as 3 over 4 n of y, and of course this is strictly less than n of y, right? So what we have here, x is equal to y times something plus yt. So here, this yt will become our remainder. And this is our quotient. Okay? And the inequality between the divisor and the remainder is satisfied here. Thus, the expression, as you remember, I put a star here, this expression, this something like division algorithm, it is really a division algorithm now, gives a division algorithm. Okay, with, let me write in merge, with the quotient here, n plus m root 2, and the remainder, what was it? Y, t, in our ring z root 2. Okay? So since we can find the Euclidean function z root 2, okay, let me write it also as a conclusion. Z root 2 is a Euclidean function with the Euclidean map n from z root 2 to non-negative integers, taking a plus b root 2 to the absolute value of a squared minus 2b squared. Okay? Do you have any questions? It is not that straightforward, but it is easy. Okay? You should just know what to show. Okay? Any questions? Is everything okay? Okay, let me continue with my second question. Now we are going to deal with this Euclidean domain. In this ring, in z root 2, show that 5 is a prime number. 5 is a prime. Okay? The first one is this one. Now, as you know, 5 is also a prime over integer, but in the remaining part of the question, we are going to show that 7 is not a prime here. Okay? But 7 is a prime in integers, but here in this ring, it is not. So let us first show that. Let me edit also here, prime, but 7 is not a prime. Okay? Now, first, 5 is prime in z root 2. What does prime mean? What does prime element mean? If an element divides a times b, okay, in the ring, then we are going to call that element as a prime element if that element divides either a or b. Okay, so we are going to show this one directly, okay, just by applying some computation. Now suppose that we are going to directly apply the definition. 5 divides a plus b root 2 times c plus d root 2 for elements from z root 2. C plus, I mean a, b, c, d are integers, of course. Okay. Now we know that z root 2 is the Euclidean domain with this Euclidean function. Okay, now we are going to apply this Euclidean function to the both sides of this division. Okay. Now using the Euclidean function n, we have 25 divides a squared minus 2b squared times c squared minus 2d squared. And this division now can be considered inside integers, okay, in z, because all numbers are integers in z. Now we may assume that since this 25 is nothing but 5 times 5, and 5 is a prime in z, then we may assume that 5 divides one of these. Five divides a squared minus 2b squared. Okay? Now, with this information, with this assumption, we are going to make a table. Now, let us consider the following table. I'm just going to look at the numbers modulo 5. Following table. Let me go. Okay, the values of AB here, the values of A squared and B squared modulo 5, the value for 2B squared, because I'm going to consider this one, A squared minus 2B squared, right? Whether A plus B root 2 is divisible by 5 means that the coefficients A and B are divisible by 5 or not, right? So I'm going to look at this one. So for the values of A, B, 0, 1, 2, 3, and 4, this is A squared and B squared. Take the values 0, 1, 4, 4, and 1. And 2B squared, of course, this is modulo 5 also. This is 0, 1, 3, 3, 1. Is it 1? No. This is multiplication by 2. 2 times this one, 2 times 4, 2 times 4, and 2 times 1. Okay? Now, as you can see, A squared minus 2B squared is divisible by 5 if and only if you apply this here, A squared minus 2B squared. Let me write it here. Also, A squared 2B squared modulo 5. This is 0 from the first line. And from the second one, this is 4. From the third line, 1, 1, and 4. So this means that A squared minus 2B squared is divisible by 5 if and only if both values, A and B, are divisible by 5. Okay? So this implies that A squared minus 2B squared is 0 modulo 5 if and only if 5 divides A, that is A is 0 modulo 5, and 5 divides B. And in this case, what we have is that 5 divides A plus B root 2. If you remember, we start our question, solving the question, by assuming that 5 divides this product, A plus B root 2, times C plus D root 2. Okay? And at the end, we have found that 5 has to divide one of them. Okay? So this means that, hence, 5 is a prime in Z root 2. Okay? Any question about 5 being a prime in our ring, in our Euclidean domain Z root 2? No? Okay. What about 7? 7 is not a prime in Z root 2. Now, can you find a factorization here such that 7 does not divide each of the factors? We are looking for something like this, right? So 7 is going to divide some product, but 7 does not divide each of the terms in the product. As you remember, this ring is consisting of all elements like A plus B root 2 such that A and B are integers, right? So 7 can be written as 3 plus root 2 times 3 minus root 2. In these kind of rings, this kind of conjugation generally works, okay? Try to consider these kind of products to obtain non-irreducible elements, prime elements. You can always use this ring, okay? So here we have to show that 7 does not divide 3 plus minus root 2, okay? Because if it divides one of them, then 7 has to be a prime number in this ring, okay? Of course, it has to satisfy this property for all possible products. that 7 divides. But here, in this case, we are going to show that 7 divides this product because it is equal, but it does not divide each of the terms, neither of the terms. Okay? So assume that assume that 7 divides. I'm going to perform it just in the same line because the norm of this applying the Euclidean function, both of these elements, gives the same result. So I'm going to perform plus and minus at the same time. So if we assume this one, then this means that there exists an element in our ring such that we can write 3 plus minus root 2 as a multiple of 7. Then there exists a plus b root 2 in this one such that 3 plus minus root 2 is equal to 7 times this one. This is even not necessary, but I wrote it. Now consider apply the Euclidean function to both sides. Okay, norm of 3 plus minus root 2 is equal to norm of 7. Without applying this one, let me first write the original one. And we know that norm is multiplicative. This norm is multiplicative. Not all Euclidean functions are multiplicative, but in particular, this one is multiplicative. Okay. Now what we have is that the norm of this one, okay, norm of 3 plus minus norm of 3 plus root 2. What is it? This is 3 minus 2 times 1 squared, right? Is it? Is it correct? I don't know. Minus. Is it the norm of this element? What was the norm? A squared minus 2b squared. A squared minus 2b squared. Okay. A squared minus, I think this is correct. This is 1. No, squared. Okay. I know that there's something wrong, and this is 7. And if you do the same thing with this minus term, this is also 7. 3 squared minus 2 times minus 1 squared, this is also 7. So let me put this one into parentheses. Now, this equality becomes 7 squared is equal to, I'm doing something wrong. No, not 7 squared. This is just 7. 7 is equal to 7 squared times norm of this element. Doesn't matter. Let me write it. Absolute value of a squared minus 2b squared. So here, what we have is that in one side we have 94. And at the other side we have only 7. But 94, this is not 9. This is 49, does not divide 7, so we have this contradiction. Okay? So this means that 7 divides 3 plus root 2 times 3 minus root 2, but 7 does not divide 3 plus minus root 2. And so 7 is not a prime in this Euclidean domain, Z root 2. Okay? Any questions? No? I think you're not listening because there was just an easy computation mistake here, but you didn't help me. Okay, that's okay. I know that I'm alone. Any questions? Any comments? Okay. Now, let us continue with our third question, and this is about another interesting ring called Gaussian integers. Now, is it the first or the second one? No, the first one. Now, this is third question. Determine all units of the ring Zi. These are called Gaussian integers. Now, this is another Euclidean domain. I'm going to give you the Euclidean function, and it is your job to check that this is actually the Euclidean map. The function n, let me call this is again another multiplicative Euclidean map. That I'm going to ask you after this question, I'm going to ask you an example of a Euclidean function which is not multiplicative. Okay, get prepared for this one. This is taking an element alpha, which is of the form a plus bi. A, b are coming from integers, to alpha times the conjugate of alpha. The conjugation here is just the one that you know from complex numbers. And this is a squared plus b squared. Okay? Taking a plus bi to a squared plus b squared. This is a Euclidean map, and this is on, of course, our ring I, Zi, and Zi is a Euclidean domain. Okay? And again, check that. This is check as a homework. Also check that n alpha beta is equal to n alpha times n beta for all alpha beta in Zi. Okay? That is n is multiplicative. Our meeting will end in 5 minutes, and after a 10-minute break, we are going to be together with the same link, okay? Now n is multiplicative. This is some easy exercise, just computation. Now suppose that what we're going to show is that we're going to determine all the units, okay? All elements which has multiplicative inverses, okay? Now first we are going to show that an element is a unit if and only if the image of that element under this Euclidean map is plus or minus 1. Okay? Now suppose that, okay, let me first write down what we are going to prove. Alpha is a unit if and only if n of alpha is plus or minus 1. Okay, we are going to prove this statement first. Then using this one, norm being plus or minus 1, we are going to determine all the units of our ring Gaussian integers. Okay? Now, suppose that alpha in Zi is a unit. Now our aim is to show that norm of alpha is plus or minus 1. Okay? Now alpha is a unit means that there exists a beta in Zi such that alpha times beta is equal to 1. Because beta is the multiplicative inverse of alpha, this means that alpha times beta is equal to 1. So what we have is that if you apply the Euclidean function to both of the sides, alpha n of alpha beta is equal to n of 1, and n of 1 is equal to 1. And we know that n is multiplicative, so instead of n of alpha times beta, I can write n of alpha times n of beta is equal to 1. Now, what we know is that norm is from our range, any range, our Euclidean domain or something like this, non-negative integers, right? So here in this multiplication, we have integers. So this equality actually holds in integers. In that. So we have two integers, the product of whose is equal to 1. And this means that each of them must be equal to plus or minus 1. N of alpha is equal to plus minus 1, and n of beta is equal to plus minus 1. Either both of them are 1 or both of them are minus 1. Okay? Now from here, as you can see, at the beginning alpha is chosen to be a unit in our ring, and at the end the norm of that unit element becomes plus or minus 1. Okay? Now on the other hand, assume that norm of alpha is equal to plus or minus 1 for alpha in Zi. For alpha in Zi. Now we have to find a multiplicative inverse to this element. Now I'm going to set an element. Let beta be equal to, what was it? N alpha inverse times alpha, the conjugate of alpha. Okay? Since n of alpha, now we're going to show the other side of our implication. And we have taken an element with norm plus or minus 1, and we consider this element, beta, the inverse of the norm of alpha times the conjugate of alpha. Now, since norm of alpha is plus or minus 1, this means that actually we do not, we are sure now that the coefficients of beta are also integers, right? Because alpha is from Zi, this means that the coefficients of alpha is from integers, so the coefficients of beta are from integers. Zi. And if you multiply now alpha and beta to show that beta is actually the inverse of alpha, let us perform the multiplication. Here, and alpha inverse, alpha conjugate times alpha, and this is nothing but the norm of alpha, right? Because if you remember, here the norm is defined as the product of alpha with its conjugate. So here we have the product of alpha with its conjugate. This means that this part is norm of alpha. Norm of alpha inverse times norm of alpha. This is equal to 1. Okay? So this means that actually beta is the multiplicative inverse of alpha. So we have proven that alpha is a unit if and only if norm of alpha is plus minus 1. Okay, now in our ring Zi, we are looking for the elements whose norm is plus or minus 1, of course. Now let alpha be in Zi, be a unit, then norm of alpha is plus or minus 1. This is nothing but, let me denote this, alpha is a plus b root 2. So the norm here, a squared plus b squared, and this is of course in integers. And in integers, the solution of this one, possibilities are, for AB, the coefficients are plus minus 1, 0, or 0 plus minus 1. This means that in the rings that I plus minus 1 or plus minus I. These are all units. Okay? Question? No? Okay. Now, an ideal, we are going to consider an ideal in Gaussian integers, and we are going to show that for every non-zero ideal in this range, in this Euclidean domain, the quotient of the ring with any non-zero ideal has to be a finite ring. Okay? This is, I think, the fourth question. Let I be a non-zero ideal of that I, prove that any non-zero ideal that I over I is finite. Okay? Now we are going to use the division algorithm, actually, use the fact that I is the Euclidean domain. We know that I is a Euclidean domain with norm of A plus Euclidean, the image of elements, bi is equal to a squared plus b squared. Also, we know that from the lecture videos that every Euclidean domain is a PID. PID means that every ideal is principal. Principal ideal means that the ideal is generated by just one element. Okay? Also, we know that every Euclidean domain is a PID. So if we take a non-zero ideal from this ring, we know that it is generated with one element. Okay? So that I being a Euclidean domain is a PID. Okay. Now, since I is a non-zero element, non-zero ideal of set I, then this means that there exists a non-zero element, A, alpha is here, in that I, such that I is generated by this alpha. Okay? Now, to count the elements in the quotient ring, let us take an arbitrary element. let a plus bi plus I is an element from this ring that I over I. Now divide, we can apply division algorithm here because that I is a Euclidean domain. Divide this coset representative a plus bi by the generator of our ideal I, which is alpha. A plus bi by alpha. Okay? And then we have a plus bi is equal to alpha times q plus r for some qr from that I, and we know that the norm of remainder should be strictly less than the norm of divisor. Norm of r is less than norm of, norm means that the image of this Euclidean function. Norm n of alpha. Okay. Now just take this r to the other side of the equality to obtain an element from the ideal I. A plus bi minus r is equal to alpha times q. This is a multiple of alpha, and alpha is the generator of our ideal I. This means that the left-hand side of the equality also lies in I. Okay? So, this means that actually you can represent this coset with this coset representative or by the coset representative R. Okay, these two cosets are equal because the difference of these two elements lies in I, means that they represent the same coset. Okay, let us write this one in words. This means that every element in Zi over I is represented by an element R whose norm is less than norm of alpha, n of alpha. Okay, and n of alpha is nothing but a squared plus b squared. Okay, now you have some number with integer coefficients, something like s plus t root 2, and you know that s squared plus t squared has to be less than a squared plus b squared, right? Okay, there are only finitely many possibilities here. Of course, there are only finitely many elements in that I whose norm is less than norm of alpha. S squared plus t squared, we are looking for integers s and t such that s squared plus t squared is less than some fixed number n of alpha. Okay, so this means that we can find only finitely many integers s and t such that s squared plus t squared is less than n of alpha, and this means that I over I is finite. Okay, and this is interesting. You have a ring that I, and you're considering any non-zero ideal of it, and you know that the quotient of your ring with any non-zero ideal is finite. And this is an infinite ring for sure, but the quotient is always finite. This is interesting. This is because this is the magic of division. Okay? Question? No. Okay. Now, not this one. Not this one, but I want to solve one more question about unique factorization domains. Just an easy one. I think this is the 5th question. Now let the ideal generated by x and 2 be I, and the ideal generated by x and 3, let us call it j, be ideals in the ring, in the polynomial ring, zx. Okay, now as the first part, prove that the product ideal I times j is generated by x and 6. Okay, and as the second part, prove that the element x in I times j, it is an element of this product, cannot be written as an element from I, an element from j. This is not always the case. X is equal to f of x times g of x, where f of x is from I and g of x is from j. Sometimes it happens. This is one of the examples. Now, first our aim is to show that the product ideal is generated by x and 6. Okay, the first one, I times j is generated by, since I is generated by x and 2 and j is generated by x and 3, the product ideal is generated by the product of the generators. Okay, naturally generated by the products, all possible products. Remember that you are in commutative rings, products of generators of I and j. So we have, we know that I times j is generated by x squared, 2x, 3x, and 6. Okay, we know that all of these elements lie in the product ideal I times j. Now, from here, we can say that we can, our aim is to show that the product ideal is generated by x and 6. So 6 is here. And if you use these two, you can write x as 3x minus 2x. So these two are not necessary. And if you have x here, this is in I times j. And if you have x in I times j, you have x times x, which is equal to x squared in I times j. These are rings, so multiplication is allowed. So x squared is not needed. Okay, so we are left with, and we cannot write x in terms of 6, and we cannot write 6 in terms of x. This means that I times j is generated by x and 6. Okay. Now for the second part, let us assume that we can write x as a product of an element from I and an element from j. Assume that x is equal to f of x times g of x for some f of x from I and g of x from j. Okay? Now, what we know is that z of x is a UFT. Okay? This means that you can factorize all elements in terms of irreducible elements up to associates and up to order. Okay? As z of x is a UFT, we have either f of x is equal to plus minus x and g of x is equal to plus minus 1, or f of x is equal to plus minus 1 and g of x is equal to plus minus x. Okay? Because x is an irreducible element. But here, in this case, if this is the case, this means that from here, 1 lies in the ideal J, and if an ideal contains a unit or the multiplicative identity, this means that that ideal has to be the whole ring. But J is just the ideal generated by X and 3, so this means that this cannot be the whole ring, right? This is the contradiction. And if this is the case, this means that 1 is the ideal I, which is the ideal generated by 2. And since 1 is contained in I, this means that I has to be the whole ring, but this is not the case. Okay? So this means that X cannot be written as a product of an element from I and an element from J. Hence, the expression above is not possible. Okay, we cannot write X as such product. Okay, any question? I have one more question about Noetherian rings. I think just a few lines were mentioned in the video lectures of your instructor. Maybe for this lecture it is not necessary to solve this question. This is just saying that if you have a surjective ring homomorphism, let me put it as an exercise to you. You just need to apply the definition of the Noetherian ring. Suppose that you have a homomorphism, a surjective homomorphism between two rings R and R prime is a surjective homomorphism, of course, ring homomorphism. Now prove that if which one? R is a Noetherian ring. Noetherian ring. Then the image of this ring is also Noetherian. R prime is also Noetherian. Okay? Let me leave this one as an exercise to you. Okay? Do you have any questions?